thermal performance under the uh, diverse operational conditions. His achievements in the engineering community have been recognized with numerous awards. He got the Outstanding Paper Award in the MTCV conference which is held in China. Also, the Best Paper Award in ICRA MMES in India. Wahidi's extensive knowledge of advanced simulation tools. He is having the knowledge of ANSYS Fluent, Thytherm, Cotherm, COMSOL, and the open forum enables him to tackle the complex engineering challenges, including the thermal, and also for the hybrid vehicles, for the thermal management to IR thermal simulations. So his blend of technical expertise, innovative problem solving, and the leadership continues to drive the achievements in the thermal engineering. Dr. Wahidi, he earned his PhD from the National Institute of Technology, Karnataka, Surathkal. Uh, so as I like give the introduction, it will again take a more time. So I'll start with this brief introduction. Dr. Tabish Wahidi, sir, I welcome you for our day 4 first session. The session is open for you, sir.
Okay. Thank you, Madhu, Dr. Madhu. It's a nice introduction. Thank you so much. And welcome everyone for this FDP program. I'm thankful to the Newton College of Engineering, the head of the department of management for inviting me for this speech and sharing the knowledge with you all guys. Already into a lot of expertise you have. I'm attending the session from last 3-4 days. So a lot of guys and expertise are coming and you all are interacting very well. So I thought I also share some the expertise what I have and what the knowledge I have achieved from last few years. So if you permit, we'll start the session. Is everything fine? Should I start, Madhu?
Yes, sir.
Yeah, thank you. Okay. So for the better connectivity now, I'll switch off the camera. If you have anything, I'll interact it later. If you have any question, you can stop me and ask me anytime. Preferably at
No,
the end
sir,
of the
our question answer session will be at the end of the
okay, so
presentation only.
okay, no issue then. Thank you. Then I'll start then. Okay.
Sure.
Let me share my screen. Let me know if my screen is visible to all you guys.
Not yet, sir.
Now?
You can share the whole screen so that it will be visible.
It's not. Option, I choose the option of entire screen. You cannot share, sorry, you have a screenplay. I'll do it again. Entire screen. Share. Loading. Visible?
Sir, yes, sir. Now it's visible, sir.
Visible
Yes,
to
sir.
all of us? Okay. Okay. So as discussed earlier, so I'm gonna discuss about the thermal management studies, what is happening nowadays in EV especially. So I'm not gonna put you on a discussion whether it is a go green conditions and whether EV will be the alternate for the IC engines, how long it will be there, and how many years will be we can have a trust on EVs. But nowadays, every OEM, whether you are belong to Hyundai, BMW, or you're talking about a Tesla, BYD, everyone is targeting the EVs. Now the market is moving toward EVs because of the lack of the the biodiesel gases or biofuels like petroleum or diesels. So everyone now trying to move on alternates. So unless until we have a better alternate, then EVs or lithium-ion batteries, people are started testing on it. So every EV, whether it's a two-wheeler or four-wheeler, come with some few sort of advantages, sort of problems. So I'm going to deal only especially about the thermal management problems. What sort of things will happen when you have a battery have a high temperature, when your battery have a low temperature, and you try to run your vehicle at a very high altitude, a very harsh condition, very hot weather, or if you're trying to run your vehicle at a very low temperature. So what sort of strategies you have to do, what sort of problem you can face when you have EV vehicles. Now, coming to the agenda, I'll give you information about introduction, what exactly it is and why we have to consider this EV conditions. Then we'll give you what will sort of simulation method. So how we can tackle this problem. Suppose we have a problem of thermal runaway, you wanted to calculate the range of the battery. So how we can do all these through simulations. Also, we do the practical testing to confirm that the simulation data, what you are coming out is very well validated, and you can start relying on that simulation. So I will discuss the simulation approach too. And I also discuss some few case studies, what we did earlier with different OEMs. Some of them even one we did very long back, so with Tesla as well. Now we are targeting with BYD. We are working with the BYD. We are working with the Hyundai. We are working with the Tata too. So we all are coming with their own problems. We need to design the battery. We need to do some thermal management case studies for them too. So I will try to conclude with some conclusion what we found. Now let us dive deeper into this. So I'll give you some introduction to the battery things now. So if you look at this very interesting thing, suppose you have a battery and it is 100% charge. Okay, people think if you have battery is 100% charge, and suppose you have 100% charge give you 100%, 100 kilometers range. Is it? Not possible. So because everything have come with some sort of management things. So out of all these things, 100% charge, even your battery is not available more than, you can't use battery more than sometime more than 85%, because you have to keep something as a buffer. What type of buffer I'm talking about? One is called as your braking protection consumption, which will fall around 5%, then generally varies from 3 to 5%. And one is called as zero production consume. What exactly the 0% consumption is? If you go, even your battery is showing you 0% charge, it doesn't mean it is completely drained out. Still, few percent of battery's charge is already there. Okay, but you're not able to find it out. So that is very needed when if you suppose your battery is completely drained out. It is always a difficult for to recharge it again. So when sometimes if you have a battery, if you remember the old batteries, if you're at home, like your acid batteries, if you throw all the acid outside your battery, your battery become useless. Sometimes we need to fill it. We'll try to recharge it again. It won't come up to the efficiency what you are already using. So we need to keep some buffer, like 0 mile buffer, something you need to keep for a charging condition. Again, if you go beyond that, your battery is not able to work it out properly. So it is very important, your battery management, how your charge is distributed, how your energy consumption is distributed. So considering all things, you can't your battery use more than 85% or 90%. So to tackle all these things, we need to very effectively how accurately your battery management thing has to be considered. And all this come with your battery efficiency and as well as your safety. The safety perspective, I'm only the safety perspective I'm talking about is thermal management case, and I'm not talking about the dropout test or edge test or something like hardness test of the battery. I'm not talking about that one. I'm only concentrating about the battery thermal safety conditions. Now, if you talk about the EV applications in various sectors, it's not only one thing that you need to consider always. I need to optimize the battery behavior. With temperature should not be very high. Not only we don't have to always consider the effect of battery will come into complete vehicle. Sometimes your thermal runaway battery problem may go in such a way that temperature is very high and it will burn out your. Suppose you are sitting in a car and your foot start feeling high heat. And there is a rule that is called as a 5-minute safety rule. If you suppose a battery start burning, it should not burn within 5 minutes. So that is called a 5-minute safety rule. So that need to be considered. Your flow temperature should not be very high. If you have electronic system around this battery getting connected, your electronic system should not get started burning. If you, because of your electric heating, there will be a case of joule heating case, where you may find continuous heating of because of transfer of current. So it may come into picture. Even suppose you are driving your car in a area where fog is very high and you need to deforest. So that, because of that, your energy start using energy consumption start using. Again, for some cases, suppose you are using your battery for cabin comfort, like you are using your battery power for switch on your AC. So again, your battery range will, your battery life, your range, everything come into consideration. So it is like a combination. It's not only one thing that is only linked here, that you're trying to only, you are trying to optimize the battery, everything will work fine. It's not exactly like this. Everything is interdependent to each other. And the only I understood that battery is only the major thing that you need to be considered. But all things, just to give you an overview, that EV is not only about the battery. It is, everything is interconnected. So it's like a full vehicle modeling. Now I'll talk about the battery model. What generally people use, have different type of modeling. So one depends on your electrical thermal behaviors. So whatever the energy of, because of energy, because of electric heating, the energy will come out. It will get converted in thermal behaviors, and these will go on hand on hand. The heat generated by electric module will get attract with your thermal module, and because of that thermal interaction, your temperature start increasing. So your battery resistance depends on your temperature and your depth of discharge. And the temperature, because of that, also depend on your resistance heating and the chemical reaction happening inside. All these, am I audible to everyone? Hello?
Yes, sir.
Okay. Just a little switch on, noise, confusion. Okay. Fine for everyone? Hope I am visible to all you guys so that we can interact each other. Okay, so your battery behaviors depends on so many things. One is your very interesting thing is your about your battery depth of discharge. So your resistance is a function of your temperature as well as depth of discharge, and heating depends on how much current is passing through this and what is the resistance it's coming out from this. So you need to balance all these two to have a understanding of your thermal management in these cases. Now, few things that need to be considered when you have a battery around. One is very important thing: what type of battery model, battery packaging you're using. Are you using a pouch level type of thing, or you're using a prismatic cell, or are you using a cylindrical cell? So all these battery have their different application, and also depends what type of battery you're using. Suppose Tesla is using a cylindrical cell. This Tata is using a prismatic cell, and other guy is using a pouch cells. Depends on the how much space they have, what type of efficiency they are offering to you, how much range they are offering to you. This depends on so many things. It's not a one thing that I'm already talking about. So when you have a battery, the thermal modeling come into picture. Everything that need to be considered based on the type of battery cells. So if you have a hybrid vehicle condition, suppose you are trying to integrate your battery with IC engines, though the modeling will be completely different, because when the exhaust gas is coming out from your exhaust system, the temperature nearby it will very high, and already you have a battery packing is inside there. So how you gonna tackle these two things so that your battery have a maximum efficiency, and you don't have to think about the thermal high temperature condition. We have exhaust is already running, your IC engine is running. Now we'll come with a few things like cooling optimization techniques, what type of cooling things you can do, how you want to balance your load. Suppose two guys are sitting inside or five guys are sitting, so mass balancing also come into picture. And a case where you have to go for a fast charging condition. Suppose you have to go somewhere urgently and you don't have time, you have to go for a fast charging condition. Because of your fast charging, the temperature goes very high. So you need to balance all these things. Okay, And one is very interesting case you may encounter through social medias or some. Now the Ola is also facing the same issue, like thermal runaway condition where your battery start burning. So that is called thermal runaway, that you also need to be considered. One of interesting thing, when you go for buying a car, people will ask what is the life of the battery, what will happen after 7 years, what will happen to after 8 years, will it work for 8 years or whether we're going to die at 6 years. That is also come into picture when you have to talk about the battery life. Then all these comes in a transient analysis, because you keep on running, your things will change with the time. And something also depends when you have a drive cycle. For the drive cycle, what exactly the drive cycle is, somebody suppose promise you that my vehicle will go, it's a single charge, it will go up to 100 kilometers, suppose. But depends at what track you are driving. Are you going uphill or you're going in a plain land? If you are going in uphill, so you can't promise 100 kilometers in a single charge. You may face maybe less. If you have a lot of turnings, you keep on pushing your brake to be on, your things will be different. So a lot of things will come in along with we have when we do the modeling of the battery. Okay, I will discuss one by one everything. So we have a three type of distribution when we do the battery for the battery modeling for the battery. One is called NTG equivalent circuits model. One is your distributed model, and one is very commonly used and well-known models, NREL. All these modules, circuit modules, are quite common when you're trying to model the battery. Everyone has their own advantage and limitation. Everyone has own disadvantage too. So let us discuss this too. Suppose if you talk about the distributed model and you're trying to compare with the equivalent model. In generally a distributed model, we need to give lot of inputs when you start the simulation. So it will demand you high. You want every input need to be given. What is the flow rate? What is the direction of what is the circuit distribution? How it is running? How the temperature is distributed? How the voltage is distributed? Everything will come into picture. Because of high detail, obviously your simulation will be very little bit so. But it's very good when you do a cell model. Very good. It will give you a complete information. Where the hot spots is coming, how your temperature is getting distributed. So for cell level analysis, it's very good. But if you talk about the pack level analysis, it's difficult for a distributed model to analyze it. So people started testing on equivalent circuit model. It required a very low detail, so simulation become very fast and well known for the pack model. And if you along with that, suppose you have a drive cycle analysis, you keep on driving a different route, you have a uphill going or downhill, you have a highway driving, or you have a city driving. So all the rash driving condition or smooth driving condition if you have, so your driving cycle come into picture, then people start trusting on equivalent circuit model. So everyone has his own limitation and it has own advantage. Now I'll simply talk about how we do the simulation approach. You must have all these information intact with you. How your speed is varying with the time, that you track it down. What type of vehicle you're using, what type of battery cell it is, what type of input you are giving, how your current is varying the temperature, what is your ambient condition with varying with time, what is your edge convection values. And based on all these distribution of current, then with people come out with the result, like how much your temperature is getting distributed with time, how your voltage is getting distributed, what is the state of charge is happening, how much temperature is coming out. It look like a very simple modeling, just you need few inputs. So coming down to the few case study that I'll discuss when we had interaction with different OEMs, and we published some papers along with them. Okay. So one of the very interesting cases, what is called as a thermal runaway. If you talk about thermal runaway conditions, where people generally feel this as a very interesting. You may find all these video in social medias when your battery start burning very high. All of a sudden temperature start very increasing, and you have like burning like anything. So smoke will come out. So when people came out with the idea of EV batteries, they don't know about this thermal runaway condition. After when vehicle came on the road, after few things happened, Then people don't come to know about this thermal runaway conditions, and they're trying to find what exactly it is and how it is. Okay, so the people used to define thermal runaway is happening when you have an unwanted chemical reaction happening inside your battery. It may happen because of your short circuit, or maybe some because of internal discharge, or you may be in contact with overcharging condition, or or it may happen when your ambient condition is very worse and you have very high temperature. So to understand this is very important. If you have batteries start burning very fast, so your complete pack will start burning very high. If one cell goes run away, it will start propagating the heat to the nearby cell. Because of that nearby cell, the complete pack will start burning. And that is very important to understand how is your heat is getting propagated from one cell to other to another, and what is the second, how much time it will take from one cell to another cell to get burned. Okay, so that is very important, and we need to understand the flow of this, and we need to come out with the mitigation technique, or we need to come out with any strategies that will help you out to mitigate this thermal runaway. So for this type of thing, I'll give you a brief information. This will be common for every interaction, whether if you're trying to understand. Just give me a minute. Okay, so for that you need to have a geometry. You may have a geometry of complete car model, or you may have a geometry of just of a battery, anyone. And you need to understand what are the few things getting attached with the battery, whether any motor is getting attached or any electronic device is also getting attached with this. So we need to understand how your battery model is, what type of battery model actually it is. It's a cylindrical cell or prismatic cell or pouch type of cell. Every battery has their own nature of burning. Depends on how much power batteries there, whether you are using 48-volt battery packs or what type of thing it is there. So number of batteries also matters, and the sequence of batteries also matter. How you arrange all this, and what type of cooling strategies have you used earlier when you're trying to predict the thermal runaway condition. Okay, these are just a condition. And sometime to tackle this, generally what we do the simulation when considering this. Your battery temperature has to be very high to understand this thermal runaway condition. You keep your gas velocity, when those after burning the gas will come out from that. This need to be considered very high. Generally, I used to keep at 100 meter, or the gas temperature will be very high around 1000, because thermal may happen after 400 or 500 degrees Celsius. Okay, then you have to define what of material it is, and why the simulation time I kept 5 minutes. This is very interesting because NCAP maintain a standard thing that your battery should not burn before 5 minutes. So this is a standard criteria. If your battery is burning before 5 minutes, that your battery is ruled out. You can't use it for the EV vehicles. Okay, this is called a 5-minute safety rule. And then sometime what we had to do is interacting how you are coupling your thermal behavior with CFD. So what we do, we start doing some pre-processing in that I call as a CFD analysis. So whatever, after doing some CFD analysis, I'll try to find it out how much gas temperature is coming out, what is your flow pattern of gas it is, what is the flow pattern of fluid it is happening. So I'll come out with a heat transfer coefficient value. I'll try to find the temperature of T fluid, then try to couple with the thermal solver. 2-3 lines of coupling I will do, and then trying to find how much time it will be. It is like a sequence. So this will be like a process automation thing, which I try to do and do to find out how much time it will take for a thermal battery to run away. So this will be I'm going to deal one case when we have a battery pack of a 24 cell prismatic cell it was, and we need to configure with as per the information given by the OEM, and what sort of electric current is flowing, how the distribution is happening, what type of model they are using, this NREL model or distributor model, that we need to configure. Then you do the symmetry or meshing for this simulation, and we try to mitigate it with, there are so many strategies to mitigate. You can provide a passive cooling system, you can go for active cooling system, you can go for a people come with a very phase of change material cooling system also come into picture. So there, and you may come up with a, suppose you come up with a solution that you change of material will be the solution for this also, or you can increase the thickness between the cells, so that suppose your thickness is very high, so time of propagation of heat will be less. So it will like insulating kind of insulation. So this case, what I'm going to discuss is the change of insulation. Here we'll try to understand how temperature is getting propagated from one cell to other cell. Okay, and what is the time of thermal runaway? How much? No, after how many minutes you might complete cell will start burning, my complete pack will start burning, and we'll try to understand which thickness will be the optimum one, so that my battery won't go run away. Okay, this is the case scenario. So in this case, along with this propagation of heat transfer from one cell to another session, I also trying to understand this aspect. This one, suppose your battery started getting very high heat temperature. Because of that, your floor temperatures will become very high. Your motor wires or motor will start getting very high temperature. Because of that, your motor may get burned, your wire connection may get burned, or your electronic system may get burned. So also we'll try to understand this scenario too, along with this runaway condition, how your battery is getting run away, how much time it will take, and what of sort of because of this runaway, how your inside temperature, your floor temperature, your motor temperature, your cable connections are getting absorbing the heat. So this is the connection. So first what we will do, we'll trigger one cell. We trigger one cell with very high temperature, suppose 1000 degrees Celsius. So make one cell run away. One cell run away, and then we'll try to find how much time the other cell will go run away. Okay, so there is a sequence of going on. Second cell, your second cell will go run away after 1.5 or 9 minutes, other will go at 2.5. So from one cell to other cell, and the complete battery is getting run away within 5 minutes. Okay, so your all things getting run away within 5 minutes. So if you look at this one, so all cells, all these are the different cells which is getting run away before 5 minutes. So this design, what we are showing to you here, is not sufficient enough. Your all cells, all 24 cells are burning within 24 minutes. So within 4 minutes. So we understood, and we tried to understood the sequence of burning of one cell to other cell. That is very important. First understand what exactly it is happening. Okay, so we understood this is happening. Now we'll start doing the calculation by increasing the thickness between the cells. Now we'll increase the thickness. It's okay. And also account with this, we'll try to calculate the temperature of your surface. How much the some surface temperature is going up. If you try to find it out, the temperature is going more than 500 degrees Celsius. Okay. Although that initial calculation, we found that if you don't have any insulation between these, so your steel layer and a carpet, your temperature will be around 500 degrees Celsius. Okay. If you suppose you put any insulating material like polyethylene foam and all between your carpet and steel, your temperature may go up to around 80 degrees Celsius. That is also a way to insulate your floor. Okay, you can still your temperature is very high, it is around 80 or 70 degrees Celsius. That is not also easy for a human sitting on this and start feeling comfortable. It's not possible. Okay, but although from high 500 to 70, that we can do this by putting your polyethylene foam insulation in between. Okay, so just giving you information that because of runaway, your floor temperature is also increasing. Now we'll try to increase it to 4 mm, the cell between 4 mm, and we also try to increase it to 8 mm, and then we'll try to compare how it will be. Now if you have 4 mm cell, okay, we'll try to understand how this cell is happening, or what is the propagation of this. If you look into this, your propagation is quite different. Okay, your burning of cell is quite different. Your second cell start burning after 3.4 minutes. Before it was 1.9, and third cell was around 1. If you remember, that third cell was around your 1.28 something. Okay, now because of increasing in thickness, your second cell start burning time will increase little bit, and this third cell is start burning after 4.8. Still your one cell to other cells burning time is not increased up to 5 minutes. So this design is not also increasing the thickness to 2 to 4 mm, also not working it out. So what we need to do, we need to increase the thickness again. So as a sequence, I started increasing from 4 mm to 8 mm. Okay. Now from 8 mm, you can feel the difference, the heat propagation from this. From one cell to other cell is taking a lot of time, more than 5 minutes to burn it out. Okay. So your second cell is not burning within 5 minutes. So with this, we can find it out that this strategy, if you keep your thickness between around 8 mm, so you can avoid the thermal runaway conditions. Okay. So just by changing different cell thickness is one of the way to to encounter your thermal runaway conditions. So just my thing is, do we have only one method to all do all these? Can we do go for a combination of that? Suppose, but by increasing 8 mm, your mass of battery will come into picture. So we need to optimize this. How we can do that? Again, so we need to come up with new strategies. Although 8 mm is sufficient enough for you to tackle the thermal condition, but your cell thickness is increasing, your complete battery pack weight is increasing. Now we need to go for another method, and we'll try to find it out. If you have a 2 mm and you have a 2 mm, or if you have a 8 mm cell, so there will be a difference of temperature, surface temperature also. Okay, the surface temperature is coming very down. Okay, it's around very less this time, and also you can protect your engine and you can protect your motors nearby electronics condition also. Okay, so these are the one method that we can tackle with. You have a, suppose you have a condition like 8 mm of condition, 5 mm safety, then you try to insulate with 8 mm, and then try to insulate it with so okay, I need to change this. Actually it is a 5 mm only. So with 5 mm and external cooling system, you can increase it to 30 minutes also. So we can optimize with balancing the things, your mass balancing as well as your electronic cooling system balancing. That is very important. When you have to balance your mass, you need to come up with a new plan. Okay, so this is a strategy that we finalize with that wall insulation of 5 mm plus external cooling system, liquid cooling system. Will help you out to increase your turn number condition, and you can go up to 30 minutes. That is what the final study we find it out. And I'll show you some just a few images how different cell pouches started burning. If you talk about the pouch cell, this will be the sequence of burning, the range of thermal propagation. If you have an insulation between this, your then you can avoid the runaway. If you have a prismatic cell, you when you this is called a jelly bean structure, and your propagation will stop. You can do some insulation between all these things parallelly. I'll give you a hint like this. If you have insulation between somewhere in between these two things, you can avoid your propagation. So this is a few example for as I explained for before. Also, this one is your pouch level and prismatic cells. Now, I'll discuss one very interesting scenario that is called a fast charging cases. Suppose your battery is very small. You are using a small battery, suppose a cell of 24 ampere hours. Because of your fast charging condition, your battery temperature will goes very high. And you take a condition that you have a city 1 hour of city driving. Again, you have to go for 15 minutes of fast charging, and you do it for 4 times. Okay, this is a case scenario for one, and you try to compare this of 1 hour city driving with the 2 hours of normal charging condition, and you do it for 4 times. Just these are due to comparison within us. When you have a fast charging condition and normal charging condition, what will happen when you have a fast charging condition? What will impact your battery life? What will impact your cell temperature? That will try to understand, and how we can decrease that will be an interesting thing for us. Okay, so if you have a battery and you try to do it a fast charging condition, generally we used to keep your battery range to be ideal operating condition will be between 30 to 20. Okay, but because of a fast charging condition, your battery temperatures are going very high. It's going up, touching up to 60 degrees Celsius. Okay, because of this, I are trying to keep you keep on doing all these things continuously, you may have come with a less chance that your battery life will come down. So your normal battery condition is suppose this much, you may lose up to 2 years or 1.8 years of this one because of the fast charging condition. Your battery life may decrease very high. Okay, so with this we can say that the battery charging causes very high temperature, that is for sure, and it is also impact your lifetime of the battery. Okay, now what we can do it, that is very important. So what type sort of strategies or cooling strategy, that is sure that we have to come with the cooling strategies when you have a case like fast charging every day, and you can't avoid fast charging because you need to run taxi every time, and then you have lot of after city driving you have to keep on charging if you, because you can't increase the size of the battery. So we need to keep on the fast charging, we need to earn more. Suppose an auto wala or something is doing the some such type of thing. So what of sort of things we need to come up with the plan. Now, one is your fast charging with along with the cooling system. Okay, suppose you provided cooling system with heat transfer coefficient of 10, and you try to do keeping your fast charging condition as it is, and you try to compare with the normal cooling conditions, and then we try to find how much we can improve the life, because it was before it was a loss of 1.8 years, so almost 2 years of loss we are losing the battery life. Okay, so with of this 10 HTC values and proper cooling system, we can increase the battery life up to 2.7. Now, not we are much closer to having a loss of 1.8 years, that we can increase the point of zero point 0.7 years more, to we can add the value to this. Okay, do we have any other method to increase? Okay, we'll check it out. Okay, with any other values, if you suppose you increase your HTC values from 10 to 20, still we can increase the life of the battery, and we can increase it to 1 year. Okay, let us change one more value and find it out. Do we have any other options? Suppose you go with 40 HTC values, your battery increased life may come up to 1.5 years. Before that, it was a 1.8 year of loss. Now you have a only loss of zero point 0.4 years if you keep on charging your battery using in a fast charging condition. So cooling improves your lifetime of the battery, and it also depends what type of cooling strategies you are using. Are you using a passive cooling system, are using a water cooling system, are using air cooling system? What is your cooling pad design, how you model it, what is the optimum design for this? Everything will come into picture when you keep on doing all these type of analysis. It's not a single thing that you come up with a design and trying to improve the life of battery. We may come up with a better design if you have a design optimization. Suppose you want to do a topology optimization of a battery cooling pad, that is also possible. Okay, to increase the battery life in a better condition. Just this example of fast charging condition. Now I'll just try to discuss some very interesting case that is called plug-in hybrid cases. In plug-in hybrid cases, you have exhaust system, and you try to mount this battery over this exhaust system, and your battery is somewhere located here. And when your exhaust system running, your battery will start absorbing heat. Because of continuous absorbing heat, and when battery will start functioning, your battery life may get impact. We need to think what sort of strategies we have to do. How, whether if because of high temperature, it may be a chance that your battery cells may go run away. So deciding all whether where should I keep my battery, that is also a better way of thinking. That all this is a very important. Where should I keep my battery? Whether it will be near to the exhaust system or away from the exhaust system, and do we have a proper space to put it in a proper way that your battery should not come or get damaged because of your any condition happening. So all these will you need to consider when you have a plug-in cases. Now, so as we try to understand why we do all these plug-in hybrid cases, just for a few things. First, suppose you have mounted your battery around, you don't have a space to mount it somewhere again. You mounted your battery just above your exhaust system. Okay, and it will look like something like this. Your battery pack is up there and all these exhausters and working. Then we try to find it out how much your temperature is coming. You try to create a fluid domain around your exhaust system and trying to calculate how much temperature is coming because of the exhaust burning. We'll try to find it out this temperature, and because of this temperature, how much because of this temperature, how much your battery is getting absorbed this heat. Okay, it's because of high temperature across your exhaust system. Then we'll try to come up with a solution How we can do it? Do we need to do we need to provide a proper cooling system around this, or one single insulation is quite sufficient enough to protect your battery? Okay. In this case, what we did, we provided an insulation around the battery that was sufficient enough to protect our battery. Okay, this were the cases, and with this, we found that the gas coming out from your exhaust system is also not hammering your battery. Your battery cells are not getting run away. Your battery life is not even getting hammered. Okay, so when you have a plug-in hybrid cases, so many the things become very complicated compared to other things. Okay. Now I'll try to give you one information, very interesting cases that is called HVAC optimization with human sitting inside. Suppose you take a scenario, when like electric bus scenario nowadays around Bangalore, any other cities, electric buses are coming and running throughout the city. So with the electric buses, what we face is a multiple problem, because one is, suppose you are switch on your AC. So because of we don't have exhaust system, something like that, so your battery consumption, uh, HVAC will use your battery power for this one, and generally what we found, generally around 40% will be taken by the HVAC system to maintain the inside temperature. Okay. And again, it's not, the problem won't stop here, because your battery is already your HVAC is consuming your battery. Apart from that, we have a lot of problem that you don't know when your system bus will stop, when your door will open, when your door will close. So that it's not like a car that you are driving, you have your own vehicle and you're driving, and you know where to stop and when to get down. But in battery, you need to have multiple stoppage. After every kilometer, you need to stop, you have to open the door, you need to close the door. Because of that, your HVAC optimization will be greatly adversely affected. And then the guys who are coming inside, you don't know about the multiple occupants, how many guys will be sit inside, what type of body size, mass, that is also coming to picture. So this scenario become very complicated when you have electric buses and you're trying to switch on this HVAC system. If you don't have HVAC system inside, it's quite okay. You can calculate that this much battery will give me this much of range. But if you have AC inside and you have multiple occupants are coming and going inside, and doors are continuously opening and closing, that scenario become very critical to analyze. So in this case, in this scenario, we need to consider two things. First, we need to understand the HVAC system that is running already, whether the man who is sitting inside feeling comfortable or not. If suppose your AC is very at very low temperature, people start shivering. That is not needed for us. It will have anyway. It is having our battery range also. So we need to optimize your HVAC system. Okay. So this case was very interesting. So we need to understand few things, like how it will be. Okay. Just example I'm giving you. Suppose multiple different body size human are sitting inside. Okay, at different locations. Someone is have a high height, someone has a fatty one, someone is a very average size. Everyone have different physiology and different body mass index. Okay, so and these based on that, and which one is sitting near to the HVAC system, which is sitting away from the HVAC system. This is also very interesting for you. And then apart from all these things, we need to understand that if say AC is switched on, what is the human comfort level is, what is his sensation level, whether he's feeling comfortable or not, whether he's feeling sweating or shivering. Those will we need to consider. So to tackle these things, to understand human behavior in the terms perspective of comfort and sensation, Berkeley, you might heard the University Berkeley, they develop a model called as a Berkeley model that is widely used all around the world by all these automobile sector to understand human comfort and sensation. Both are different. You don't think this both are same. Sensation and comfort are different. I give you an example. Suppose you are in a summer day, you are outside. Okay, you're outside. You suddenly you enter your home, and your AC is around 16. All of a sudden, when you entered your home and your AC is at 16, you will start feeling comfortable, very comfortable. Although your AC is at very low temperature, but you start feeling comfortable. But after few time, after some time, but your sensation is very high. You're feeling comfortable, but sensation is very high. Okay, we are receiving very sensation is very high, but you're feeling comfortable. After half an hour or 15 minutes or 20 minutes, you start feeling shivering. Okay, so you are feeling started you'll start feeling uncomfortable. So your sensation and comfort both are different, and it depends on so many things. What is your body mass index, where you are standing at, what is your activity you are doing, how, suppose you are doing exercise, and how long you are doing exercise, what type of clothing you are wearing, and what is your body's size, and which gender you belongs to, whether a male or female. Okay, this everything will come into picture, and based on that we'll find this every human have different response level. Every human has a different way to, some will feel start shivering, some will start feeling sweating. So everyone have different, you can find this in this image, that everyone have a different. This one start feeling very low temperature, the man sitting uh, bag is little bit hotter. So it depends on what is body mass index. This is the image where you have a different body mass index, 15%, 5%, 95%. So everyone has a different level. And the man who is sitting here is feeling hot at leg. So this need to identify. So considering all these cases, we also need to do this exercise for the bus. Same thing. Suppose a bus filled with a different occupant, and you try to understand human activity and what is the comfort level for man sitting backside, and considering an average height all around, or what will be their sensation level, and what will be their comfort level, whether your driver will feeling comfortable or not, or the passenger are feeling comfortable, where your HVAC system need to be located just in front of your driver, or just away from the driver little bit in angle from the driver. That is also matters everywhere. If suppose your AC is just in front of driver, the air blown from it will may disturb your driver while driving, or it might just air coming out will be so low that with people driver start feeling chill. So it may disturb your it will affect to your complete HVAC system, and may also affect to your well, a driver getting disturbed, the whole things will get disturbed. So that will we need to understand. Based on that, we can suggest what will the in-cabin condition for if you have a bus and HVAC your bus is using for to maintain that your battery consumption is getting being used by your HVAC system. So all these is a very complicated case that we did it for one OEM. Now I'll discuss one scenario that is called drive cycle scenario. And this is very interesting. When you try, you have, in generally we road, we count how much is the mileage of your vehicle. Depends also how you drive your vehicle. If you have a rash driving, your mileage is less. If you have a smooth driving around 40, 50, your mileage will be very good. So also depends, the battery also behave in the same way. So suppose your driving pattern, your speed is continuous changing. Okay, you are driving the city or you're driving in a highway. What are your battery parameters, how your driving pattern is, and what is the weather condition there, whether it is a hot day or it is a cold day. Okay, no, and what is the EV parameters you have, what is the size of battery, how much power of the battery is, what type of battery it is, whether cylindrical pouch or whatever battery it is. So everything you need to consider, and then based on your driving pattern, driving style, we can finalize whether whether this is sufficient for you or not. Now, for that case, suppose check a scenario. Sorry. Check a scenario. You have a uphill type of condition. You're going here, and you try. Somebody promise you that at one charge you can go up to 100 kilometers, but you have a driving condition of is a very uphill condition. You may need to just suppose you are going 200 kilometers. After at a single charge, you may battery your discharge after 80 kilometers only. So you need to find after how many kilometers I need to charge my battery. Where should I stop and find a charging station? That is also important. And it also depends. Suppose a case where suppose in the whether you have a regenerative system. Suppose in some vehicle we have a regenerative braking system where you give your battery will get keep on charging. Okay, So that also matters. If your battery, because of your charging your battery, because of braking system, your battery get to start charging. That also come into picture. So if you have different condition, like your whether you have without braking system, if you have with a driving system, okay, then based on all these inputs, you will take all these input, you get the profile of your driving cycle, then you import this data. You may require a MATLAB tool or some other tool to understand this one. Then you try to fit it to data to your battery system. You try to calculate how much how the current is flowing, what the temperature is coming out, how much your battery, how much after time your battery get discharged. All these will help you to calculate and you understand what will be your range of the battery, what will be the health of your battery, what will be the life of a battery, what is the nature of a state of discharge or state of charge. All thing is very important. We have a drive cycle condition. So these are the method that sometimes if you have a lot of things, parameters are changing continuously, you need to do the process automation. And it is a way to automate your things, and you can feed the data continuously with different drive cycle conditions. And this will help you simultaneously will run with your thermal solver or CFD solver, came up with the data that will integrate to your from one MATLAB solver or a CFD solver to Python solver or thermal solver to understood the temperature of the life, temperature of the battery, life of the battery or range. So we can do the process automation so that you will your simulation will complete very fast. You will get an overview idea of how will be how much the range of this one. So with this type of thing, this is just a flow pattern or a drive process automation chart that I'm showing to you. And based on that, you can predict the in-cell temperature with if you have a with cooling system, without cooling system, how if your ambient temperature is varying. So what will your life of the battery, how much range of your battery, what is your condition there. If you are suppose you are driving in a very cold condition and I'm going uphill, so battery life has a different will be a different thing. And if you have a doing running the same battery at a third desert, your battery life may affect differently. When you have a cooling system, the battery temperature will little bit higher. Okay, so all these weather condition, your environmental geographical condition, your road pattern, your drive cycle will help us to understand the life of the battery, range of the battery, temperature of the battery. So everything is goes one on one. So okay, with this I'll try to stop my presentation. If you have any question, please go ahead. I'll happy to address. Yeah. Hello.
Yes, sir.
Yeah. If anyone have any question, ask question. I'll try to answer it out.
Uh, just a minute, sir. Uh, participants, if you have any questions, please you can ask. Otherwise, sir will continue. Dr. Tabish, you can continue now.
So almost everything is done from my end. If you have anything need to be asked, I'll happy to address all this. My presentation is over. I kept 15 minutes buffer for question answer sessions.
Hello, sir.
Yeah, Manish, please go ahead.
Sir, as you have shown in your slide that there is time delay between different cell. So have you tried with different material? Now, what kind of material have you used for the cell? Outer bound material.
Then that what I have shown you, it was a case where we have a same material. I'll try to increase the thickness of the material. Okay, and in a for a float condition, suppose because of your charging, your float temperature is also increasing. So generally we have a carpet and a steel. Okay, so in between we kept one insulation element that is called material that is polyethylene. Okay, foam. that reduces the temperature very, it's a very good insulator. So we found very less temperature in that case. Hope I'm clear to you. Yeah, Nitish, do you have any question? I think. Yes, Arvind?
Hello.
Yeah, Satish. Go ahead.
Sir, I have one question.
Yeah,
Actually, I
please.
don't know whether that question is correct or not, but I have that question.
Yeah, please, no.
Sir, during the fast charging, battery fast charging, I think in your PPT you are saying that we need a cooling system for the battery cooling purpose.
Yeah.
So for that cooling, which type of energy we need to require, and by using that energy, whether the battery efficiency is going down or any effect is there? Because
Okay.
whatever the energy we are using, that is from battery only, I think.
No. What exactly? I'll tell you the scenario. Because of fast charging, the temperature of cells are increasing very high. Okay. If you keep on charging your battery, and suppose your battery, you are in condition that you need to charge very frequently, because your battery size is small, and you have a long drive condition, or you have you can't increase your battery size, so you need to frequently charge your battery. If you keep on doing the frequent charging, your battery life may decrease because of the high temperature. Okay, because your battery start losing life. To avoid this condition, we'll come with the solution that you need to provide a proper cooling so that your battery temperature won't go up. So to provide a proper cooling system, we need to give a path to the flow, and it also depends on how you manage the path of the fluid to flow through the battery. One is very important. Design a flow path, and what type of what type of fluid you are using, whether you're using active cooling system or passive cooling system, or you're trying to cool everything through your air cooling system, or you're trying to cool with any coolant system. That every thing will matter. So all these life depends on your cooling strategies. Okay.
So that cooling is must be at the time of battery charging only.
No, that also required when you are using battery also. Some, because if discharge, in that discharge condition, battery is also getting heated up.
So if we are using the regular time using the battery, so at that time we are using the power for the cooling for the battery only, na?
I didn't get you, sir.
So suppose we are using the cooling system
Yes.
in regular time, whenever we are using the charging or whenever we are using the vehicle, so at that time, so that energy required for the cooling is nothing but the we are going to take from the battery only.
That is there.
That is enough. So that will be
That's also depend on what exactly you're using. Suppose your battery is designed for air cooled.
Okay.
It is getting automatically cooled.
Yes.
Depends. And suppose you have a fluid cooling system, then you need a push the fluid to flow continuously.
Okay.
For that, the energy used by the cooling system is very less. That's why in the starting slide I told you that suppose your battery is 100% charged, it doesn't mean you may not gonna go at 100 kilometers. There are inside, we need to consider there are some buffer things. So you can't use battery if it is less than 10% charge. The battery is going down. So you need to stop if it is going 10%, below 10%. So all these factors come into picture. There are zero mileage charges. There are some condition like you should not charge your battery less than, you can't discharge your battery less than 10%. So everything will be into picture in that cases. Yes,
and what is the status of the material, sir, that we are using for the battery? So if we are using the high heat transfer rate type of material, so it will be required the less cooling type of, is anything is there for the battery material?
Battery, a lot of guys are coming with a combination of the battery. We call this a lithium ion, simply lithium ion, but it's not exactly lithium only. So the base is lithium. Then there is nickel come into picture, 5% of nickel. Then people add iron particles. They are putting some other things into picture. So many things come into when you design the battery, and depends on people with different mixtures. Like it's like I can call it in the form of raw man. It will be like alloy type of thing. Okay, and you have adding keep on things and some percentage decide. and people come with different material even now. People started using carbon materials, some insulating material in between based on their application and their research areas. So a lot of things are there. It's not a thumb rule that you have to only use one thing. It's not a way. That's all. The keep on research is going on, keep on because of this only.
So that cooling system is inside the battery or outside the battery?
Depends.
Depends on it.
If you have batteries packed like this,
Okay.
you don't have an option to provide a cooling system. Then your cooling system will be below with this.
Okay.
If you have a sufficient space, then you can have a very fine channel.
Mhm.
I'll show you one diagram that is very interesting diagram. I'll give you an example. Just I'll share the screen again. I'll give you how the Tesla, we designed our Tesla. It's very interesting. I'll give you one example. I hope my screen is visible. 1 minute. Let me know my screen is visible. It's very intricate design. It's very difficult to design even. Okay. Hope 1 minute. Look at this design. Is it visible for all you guys?
No,
This
sir.
one. This one. Visible?
No, sir.
Still not. What is happening like this? I need to stop. Yes, press. Stop sharing. Alien share. Sorry, an error had been occurred when getting this right. Why is happening?
You
have a
can
permission?
share the full screen. So
That's I'm doing. Okay, I'll do it again. Sorry for my side. Okay, 1 minute. Okay. Check my entire screen. No, I think it will be. Yes, again, I'm getting the same problem. Yeah, is visible now.
no,
Not.
you click on the entire screen, then you click
No,
on
I
the
am doing the same thing. Entire screen.
screen which is in the window which you see
A window.
the whole screen.
This present
Click
now.
on that and share.
Present now option is there, right? That I need to click, right?
Then the entire screen.
And then
Click
you
on the
go
entire
to
screen. After that,
entirely.
you will see the all participants logins. So on that, you just click
and then share, right?
then share.
Okay. Again, I'm getting an error that occur when share screening. Maybe you stopped giving a permission to share or something.
No, you can share. So.
Is it visible? Not yet. No. Something problem is coming out, sir.
Okay, sir. No problem.
Okay, I'll share that diagram too. Okay, am I visible to all of you guys?
Yes, you are visible.
Okay. Okay. So this very complicated design, and the plate was designed so in such a way that it's like look like a plate. You can't find this like a flow pattern. This was very minute pipe are going like the macro channels, and they merge in between the cells. Instead of going below that cell, they merge it between the cells, and it was very effective cooling that increase. And they are using for Tesla S.
Okay.
It was used. Now they come with the Tesla Y. So many things are now BYD. You can find BYD is very high competing with Tesla already. Started capturing the market of Asia market now. In Bangalore, I find 2, 3 BYD, and the BYD showroom is near my office also. So that things are and the vehicle is very good look also.
Sir,
Okay,
one more last question, sir.
Yeah, sure.
I think in the beginning slide, you are saying some result, like if we increase the some gap, like a 2 mm, 4 mm, 8 mm. So what that exactly the gap, and how that exactly gap is going to affect on that particular?
It's not exactly. Suppose this one cell is having other cell getting attached. Okay, this like this. I hope I am visible to all you guys. Like this. If you try to increase the thickness of this one, okay.
Cell thickness.
Cell thickness.
Okay.
So because of cell thickness, from 2 mm to 4 mm, 4 mm to 8 mm, you can stop the propagation of heat from one cell to other cell. That is also a way to avoid your thermal runaway condition. But it will come with a picture that your cell mass, your complete pack mass is increasing. That is the adverse effect of this. And
Mhm.
it may hammer your range of the battery too.
Okay.
Okay, already 5 guys are sitting. If all 5 guys have a less weight, your battery will be high, range will be high. And your battery, that's why the fine EV vehicles are not coming with the metal things. They are coming
Mhm.
with fabrics and like or not fiber materials. Okay, except few areas, because they don't want the weight of the EV to be very high. Otherwise, it will impact your range.
Okay. Okay.
So just balancing so many things. It's not only one thing that you have to balance. Only run away. Only the problem is I see there's so many problems. That mass is very high things, and the
Mhm.
guys who are sitting now HVAC system, your electronic device system. That all will depends on your battery consumption. If you have a lot of electronic device, people think, oh, it's both a chair, it's fine running very good. We have a lot of features inside, but the battery range will get impact. People don't know that.
Mhm. So nice work and very interesting work. Interesting work you are doing, sir. Thank
Yeah.
you for your nice presentation, informative presentation. Thank you, sir.
Thanks.
Tabish, I have a question.
Yeah, please.
As we know the cooling of the batteries, okay, so we are using the different coolants for the BTMS, right?
Mhm.
Means are you working on the coolant side or
No,
like
no,
something?
this coolant depends. People have started using so many coolants nowadays. Even for I suggest we can go for supercritical fluid coolant. That will be very
Yeah,
effective.
that's what my
I
question. Like
recently I had a discussion with a team sitting in India, so Hyundai team, and we met them. They started telling that this is the thing that we need to capture or trying to find out any effective cooling system that will manage very easily for us, and easily we can do all this cooling effectively. Then I suggest them you can go for supercritical fluid cooling. That we can also manage. It's not a big thing.
yeah,
That
because we are working on CO2. CO2 again, we have the a very good thermophysical
That's
properties.
only
And
thing is how we gonna balance the pressure and the thing, that because for effective cooling you need to be your more than your 75 or 73 bar for a supercritical condition.
yeah,
So everything will come with the advantage and disadvantage. We need to see how you're gonna balance all this effective cooling with pressure balancing.
so that if we use the CO2, it will be like again the mitigation of the climate things, CO2 and the climate change, and it will be very cheaper, right? So as
Uh,
here
we
with the
can use the
battery,
we can use the carbon capture
normally for
technique
the
of
normally
this.
for the EVs, people or even the OEM, they say that the battery cost will be more after maybe 5 years or maybe 6 years. Okay,
It
so
will be
again
there
with
or
the
not or not. To be very honest, um, before what we have a company name as Forvia. They are only manufacturing the exhaust system. From last 3 years, before that, after COVID and all, they stopped manufacturing the exhaust system because people moved from exhaust system IC engine to a EV system. Now everyone OEM is targeting EV.
yeah.
Now this year, last from 1.5 year, Forvia bounced back and they started talking to us that we have to work with exhaust system. I asked because why you guys are working again in this EV, because already exhaust no one is using exhaust system. So the GM of that company told, wait and watch, sir. This is the only solution for everything. EV won't work for long. The people, all those are making for the green, go green, and all zero emission technique. It won't be there. And the biggest problem with EV is how you gonna dispose all these batteries, because it's not easy to dispose in the environment also. So, and if anything happens, it has EV batteries have self burning attitude, because they have lithium ions have the oxygen inside. If a little bit of a spark is also there, the complete cell start burning. So many things are there. People are working on it, and you may be find out or add hydrogen to be a alternate in few years, where you have we can handle with this.
Uh, okay, sir. One more question is, right now we are using the lithium-ion batteries. Even I think you might have seen the Tesla is coming up with the aluminum-ion batteries.
And that all, sir, what Satish is asking about now, the mixture of this thing. Lithium is the base of it. You can add aluminum, you can add nickel, you can add any iron material, you can add any combination to increase the life of the battery or the strength of the battery. Okay, everything is keep on adding. People doing research on the materials and keep on adding all these things. There's so many researchers going on. It's not the initial battery what have been made in 2010 is the same battery that we are using, but the base thing is same. It's a lithium ion battery.
Okay. And one more question is, even nowadays for the EVs, we are discussing about the solid state batteries. So can you throw some light on the solid state battery?
Solid state battery, still we need to find out what exactly it is and how we're going to do research on it. But okay, people started using some phase change material and using some other techniques to do this. Okay, so solid battery materials are different that need to be even have to gather much more information in this.
Okay, sir. Thank you. Sir, Chitragar sir, do you have a question? Participants, do you have any?
Nitish, Arvind had raised their hand. Yeah, Arvind, go ahead. Yeah, Parshuram sir. Hello.
Hello.
Chitragar sir, your
Hello.
voice is not audible.
Yeah, I'm in traveling mode. Maybe I may
Yeah,
come across
you're
with
visible.
connectivity problems. Shall I ask the question in
Yes, sir.
next session?
Yes,
Now
sir.
you're visible.
Yes.
Thank you. Thank you.
Maybe he is having the
Connection
network
issue.
issue.
Any other guys?
If anyone have the queries, please you can ask to Dr. Tabish.
One from Nitish is trying to ask something. Raise your hand, then Arvind. Okay, these two guys. Okay. Okay, so shall we
Yeah, you
stop?
can unmute your mic and you can ask the question. Participants. Okay, I think
Yeah.
all the participants have understood your battery thermal management very good, sir. You have given the extensive session regarding this battery thermal management because nowadays, as we are aware regarding the EV, everyone talking about the burning the batteries or the whatever the side effects happening with the EVs also. So really, we have thrown a light on all the aspects like how the battery cells and what will be the material and how we can manage the battery temperature along with the like the curb weight of the vehicle, the passenger, everything. So it was a really nice session, Dr. Tabish. So once again, I would like to thank Dr. Tabish Wahidi giving us his valuable time for this FDP and explaining or the delivering the session. So I would like to thank from organizing team. Thank you very much, Tabish.
Thank you so much. Thanks, Northern College, Madhu, and your head of department, all the guys who organized this. It's very interactive session, and you all guys are doing very well. All the best for your the college and all the things.
Yeah, thank you very much.
Thank you so much.
Dear participants, within 2 minutes, we'll start with the next session, second session of today. So, which is on the topic of development of Savonius turbines for the hydrokinetic energy generation. The session will be delivered by Dr. Shashikumar CM. So within 2 minutes, we'll join the meet and we'll start with the session.
Okay.
Right, sir? Is it audible?
Yes, sir. Audible, sir.
Also audible.
Yeah. Sir is working as an assistant professor in the Department of Mechanical and Industrial Engineering at MIT, Manipal. He earned the Marine Technimont postdoctoral fellowship in the field of food waste to hydrogen through steam methane reaction using the CFD analysis of different nickel catalyst sheet from NIT Surathkal. Also, he pursued his PhD in a novel design of the hydrokinetic energy, which deals with the turbine from the NIT Surathkal. Master of Technology in Thermal Engineering, again from the NIT Surathkal. I think he's the from baby to adult. Everything he has done from the master to the postdoc from the NIT Surathkal and bachelor from the autonomous engineering. He is having more than 15 years of teaching experience at various institutes, and he have the so many achievements as a best thesis achievement award as well as the best paper awards at a different symposiums, conference, etc. And he also got the Forbes Marshall Outstanding Project Awards in 2024, entitled with the experimental investigation of vertical axis hydrokinetic turbines. He's having more than 15 Q1 journals on his name. So actually, the Shashikumar sir is working very extensively in a research area. He's also having the more than 10 international conferences, and he filed more than 3 patents. Out of that, one got granted. So as I told earlier, he is the man who is really working in the hydrokinetic energy in turbines, so that we can utilize the energy and also we can reduce the energy which it is consuming. Okay. So Shashikumar sir, I welcome you for this FDP. Now the forum is open for you, sir.
Okay, thank you, Dr. Madhu Biradar, for giving a brief introduction. Good evening, respected professors and participants. Today I'm going to
Hello.
1 minute. Is my PPT is visible?
No, sir. You can share the entire screen. Present now, then entire screen, sir.
I'm unable to share my PPT. Now
Just
it
a
is
minute.
visible.
Yes, sir. Yes, sir. It is visible. You
It is
can.
visible now.
Yes, sir.
Okay, good evening, one and all. Today I'm going to discuss about the topic of recent advances in vertical axis turbine for small scale hydropower applications. And this this turbine is specifically for small scale hydrokinetic power generation. Because in the last 3 days, many resource persons already discussed about the green energy, what is the use of renewable energy sector, as well as the why it is required to reduce the emissions and all. In the recent year, there is a demand of energy. Renewable energy is required to increase the renewable energy sector. Various renewable energy sectors are available. In this picture, we can see the various types of renewable energy sectors, such as solar energy, as well as the biomass, geothermal, wind energy. Coming to the hydrokinetic turbines, tidal energy, as well as wave, and also the hydrokinetic turbines. So these are all comes under the renewable energy sector. This is the data taken from the MNRE. In this, around 136.57 gigawatt of energy obtained from all the sources. Around 88.4% energy obtained from solar as well as the wind turbine. Coming to the small scale hydrokinetic turbine, around 3.66% of energy coming from the small hydrokinetic turbines. So this is the data from till February 2024. This data taken from the MNRE website. These are the status of hydrokinetic turbines installed in India as well as the outside India. These are the list of locations as well as the type of turbine installed as well as the capacity. Location wise, the state wise, Dehradun, as well as they installed the axial flow type of turbine with a capacity of 25 kilowatt. The application for the rural energy applications as well as the Tamil Nadu, Kerala, West Bengal, likewise different types of turbines they have installed, like axial flow turbines, vertical axis turbine, cross flow turbine, horizontal axis turbine by various states. For small scale electricity generation, the capacity is ranging from, for the case of Uttarakhand, 25 kilowatt, as Tamil Nadu around 4.4 into 5 kilowatt. These are the various capacities installed in various states. And also coming to the international status of installation of the hydrokinetic turbine, this data is taken from the literature. The country-wise Canada, as well as the France, UK, United States. These are the different capacities of hydrokinetic turbines installed. As per in the case of rivers, irrigation channels, various zones to generate the small scale as well as the small scale electricity generation. Various types of turbines are installed: cross flow turbine, axial flow turbine, horizontal axis turbines. This picture shows the various types of turbines. The turbines, you already know the different types of turbines, mainly classified into two types. First one is the axial flow turbine. The second one is the cross flow turbine. The axial flow turbines are already mainly classified into two types: the horizontal axis as well as the inclined axis turbine. This is the various pictures of the various types of turbines. Solid mooring turbines, buoyant mooring turbines. Coming to the cross flow type of turbine, the cross flow type of turbine having more advantages. The cross flow type of turbines is mainly classified into two types, that is a vertical axis as well as the in-plane axis. The vertical axis turbine is mainly classified into various types. In that, Darius turbine. Darius turbine is a one of the lift type of turbine, and also a helical type of turbine, as well as the Savonius turbine. So out of these, Savonius turbine having very good advantages. Savonius turbine is a one of the type of turbine. It is a drag type of device. Because of due to the pressure difference between the two blades, this turbine will rotate. We can extract the energy from wind as well as the water. Actually, this is a type of wind turbine. So this can be used as either wind turbine as well as the water turbine. The water turbine we can install this type of turbine in the case of river as well as the irrigation channels. More advantages in the case of irrigation channels, because in the case of irrigation channels, the movement of flow in the only one particular direction. There is no disturbances in the case of river compared to the river. So we will get the good amount of velocity in the case of irrigation channels, like up to 2 meters per second velocity we will get, so that we can extract a good amount of electricity. We can extract the good amount of energy with the help of irrigation channels. This is the a 3D model of the Savonius turbine. The Savonius turbine, this is the front view as well as the isometric view of the Savonius turbine. It consisting of two advancing blade. One is advancing blade profile, and another one is the returning blade profile. In the top view, this look like a letter S, capital S. It consisting of advancing blade profile as well as the returning blade profile. Total height will be the HR will be the height of the turbine, and also it consisting of two plates, top plate as well as the bottom plates. The advantage of top and bottom plates I will explain in the next slides. To improve the performance of these kind of turbines, Savonius turbine, various design modification is required to improve the performance of the Savonius turbine. These are the various design parameters of the Savonius turbine, like aspect ratio, overlap ratio, separation gap, and with the use of the end plates. By using the multi-staging instead of single stage, we can use a multi-stage by increasing the number of blade profiles. And one more important parameter to increase the performance of the Savonius turbine with the use of augmentation technique, and also by modifying the blade profiles. Coming to the first important aspect for increasing the performance of this kind of Savonius turbine is with the use of the aspect ratio. The aspect ratio means it is the ratio of the height of the turbine to the diameter of the turbine. As the aspect ratio increases, suppose if we install these kind of turbines in irrigation channels, irrigation channel having a very good depth of water, so that if you increase the aspect ratio more than 1.8, so that we can extract more kinetic energy into electricity, so that the higher aspect ratio is recommended. Suppose if you are using these kind of turbines in the case of irrigation channels. The H is the height of the turbine and D is the diameter of the turbine. The aspect ratio, it is a dimensionless parameter. The second, these are the various aspect ratio, turbine having the various aspect ratio ranging from 0.5 to 2. Another advantage is of using the lower aspect ratio. Suppose if you use the lower aspect ratio, the torque generated by the turbine is higher. If you use a higher aspect ratio, the turbine will rotate at higher RPM. If you use lower aspect ratio, we will get the more torque. Based on the application, we can use the different types of aspect ratio. So another important parameter to increase the performance of this kind of Savonius turbines by giving the overlap ratio. In the previous case, there is a turbine is not having any overlap ratio. The overlap ratio means there is a small gap between the advancing. This is the advancing blade and this is the returning blade. So that we will provide a small gap between the advancing blade as well as the returning blade, so that the whatever the fluid, either it may be air as well as water, whatever the fluid enters the advancing blade, the some part of the fluid will impinging on the returning blade profile, so that the overall efficiency of the turbine can be increased with the help of the overlap ratio. Another some optimum value of overlap ratio is required because, so this is the schematic diagram for the turbine having zero overlap ratio as well as the turbine with overlap ratio. Suppose if you increase the overlap ratio by giving the gap between the advancing and returning blade profile, whatever the fluid enters, that will not hit the advancing blade profile, it will directly hit the returning blade profile, so that the turbine performance will reduces. So that the optimum value of the overlap ratio is 0.15. That is the best optimum value for getting the good performance with the use of overlap ratio. So coming to the next design parameter, that is by providing the separation gap. The separation gap means that there is a gap between the advancing and returning blade profile. This is the gap provided between the advancing blade as well as the returning blade profile. In this case, if you provide the gap between the advancing and returning blade profile, whatever the fluid enters, that will easily pass through the gap. This fluid will not impinging on the returning blade profile, so that the turbine we cannot get the good performance if we give the separation gap. So that it is not recommended to give the separation gap between the advancing as well as the returning blade profiles to get the good efficiency. So that without the turbine, without separation gap will give the better performance compared to the with separation gap. So next design with the use of end plates and without use of end plates. Suppose if the use of end plates, it will work as the fluid will protect within the turbine, so that the end plates is one of the thin circular plates having a negligible thickness. It is provided at the top as well as the bottom side of the turbine blades. The addition of end plates in the Savonius turbine will increases the coefficient of power as well as the torque. So this end plates will inhibit the fluid, so that it will protect the fluid during the rotation of the turbine, so that the efficiency of the turbine can be increased by using the end plates. The thickness is almost similar to the thickness of the blade profile. This is the pictorial representation of the turbine with end plates as well as the without end plates. The two end plates are shown in this diagram. So coming to the another design with the use of multi-staging. Suppose with the use of multi-staging at some angular position, for example, around 100, and during the rotation of the turbine blade, at some angular of rotation, the turbine will give the positive torque. At some angular of rotation, the turbine will develop the negative torque. So that the multi-staging, we can increase the performance with the use of multi-staging. This is the schematic diagrams of the turbine with the multi-staging, single turbine with plates, and single turbine with two plates, as well as the two-stage, as well as the three-stage turbines. For all the cases, end plates are provided. The angle between the first turbine to the second turbine is around 90 degree, and second turbine to the third turbine is 90 degree. This is the very important technique to improve the performance of the vertical axis turbines. This is the very important technique, that is by because Savonius turbine consisting of two blade profiles. One is the advancing blade profile, second one is the returning blade profile. So advancing blade will give the positive torque, and returning blade will give the negative torque, so that during the rotation, at some angle of rotation, the turbine will give the negative torque, so that the overall performance of the turbine is reduces. To improve the performance of the turbine without modifying the blade profile, this is the one of the technique to improve the performance of the turbines by using the augmentation technique. These are the various augmentation techniques developed by the various researchers. The first one is with the use of curtains. The curtains means the two plates will be provided in front of the turbine blade. These are the two plates. This is for the case of wind turbine. Wind turbine, the two plates will be provided in front of the turbine, so that whatever the fluid enters, that directly enters, it will directly hit the advancing blade profile, so that it will not hit the returning blade profile. There will be no negative torque. There will be no negative torque. Therefore, the overall performance of the turbine can be increased. This is the one of the technique developed by the researchers. With the use of curtains, we can open and close. We can place the curtains to desired location to get the optimum results. The second technique with the use of obstacle. Obstacle means a small plate will be provided in front of the turbine, so that in this case also, the second case also, by using the obstacle, whatever the fluid enters, directly hit on the advancing blade profile, so that the overall turbine performance can be increased with the help of this obstacle. This is a small plate will be placed in front of the turbine blade. Next, coming to the third design by providing the nozzle, the ducted nozzle. This is a one of the type of configuration known as a nozzle configuration. So in this, a small duct is provided. This is a convergent duct, so that the velocity of the fluid is always already increased, so that the high velocity will hit on the advancing blade profile, so that in this case also turbine performance can be improved. So with the help of this is a ducted nozzle configuration. This is the another configuration is similar to the previous case, ducted nozzle case. In this direct nozzle kind of plates, the plate will be placed in the form of nozzle position, the conversion section. In this case also, in all the cases, the fluid, either it will be wind as well as the water, directly hit on the advancing blade profiles. These are the various configurations developed by the various researchers to improve the performance of the turbine. This also similar to the previous case by using the deflector system, and also the conveyor system, and also another one is known as circular windshield. In the case of circular windshield, the small arc type of plate will be provided, so that the fluid directly hit on the advancing case. And this is the control of wind direction. In this case also, the direction of the fluid will focusing only on one particular bed profile. This is the these are the various techniques which is used to improve the performance of the Savonius turbine by using the one of the best technique, that is known as the augmentation technique. By another design by to improve the performance of the turbine by increasing the number of blades. This is the example for the 2-blade turbine as well as the 3-blade turbine. In the case of a 2-blade turbine, it consisting of one advancing blade profile and one returning blade profile. In the case of three-blade profile, so 3 blade will be provided. In this one, this is the advancing blade profile, and remaining 2 will be the returning blade profiles. These are the various configurations, and also to improve the performance of the turbine, augmentation technique is the one of the best technique to increase the performance of the turbine. Suppose without using the augmentation technique to improve the performance of the turbine by modifying the blade profile. So by modifying the blade profiles, we can increase the performance. Since the turbine is consisting of 2 semicircular blade profile, so that the drag force on the returning blade profile will be higher. So that instead of using the semicircular blade profile, we can modify the blade profile into various shapes to get the better results. These are the various researches carried out, either experimental as well as the numerical studies to get the better results by using the modified Savonius turbine. This is the first case is known as modified Savonius turbine. They modify the blade profile. This consisting of the small arc. This arc is around 124 degree, and a straight line will be there here, the straight profile, and also one more curvature is provided. So in this, they increase the performance of the turbine compared to the conventional bed profile. So this is the 2 semicircular bed profile. It is also known as a conventional bed profile. Conventional bed profiles developed by a French engineer known as Savonius. It is initially it was a semicircular bed profile. Later, various researchers modified the semicircular blade profile into modified version to improve the performance of the turbine. So next one is by modifying the blade profile into S type, developed by Ramadan. They converted the semicircular blade into a small curvature kind to improve the performance. In this case also little bit improvement obtained compared to the conventional blade profile. So another one is known as electrical turbine. In the electrical turbine also, the little bit improvement was found by the researchers compared to the conventional blade profiles. So various researchers carried out the various investigations by using the experimental investigations or numerical investigation to improve the performance of the turbines. Various parameter studied. The first by instead of using the horizontal channels, suppose if they use the inclined channels, because in the inclined channels the water will be flowing at very high velocity, so that we can convert the hydrokinetic energy into electricity. More energy will be available on the slope side, so that we can get very good conversion of hydrokinetic energy into electricity. This is the one of the best method to improve the performance of the turbine. Instead of installing the turbines in the horizontal, the flat kind of channels, if they install this kind of turbines on the slope channels, so that because of due to the inclination, the water will be moving at higher velocity, so that the higher conversion efficiency will be obtained by installing the Savonius kind of turbines in the inclined channels. And also by providing the taper, by providing the various researchers as developed the turbine, the both top and bottom side of the turbine of having an equal diameter. in the bottom as well as the top side. Instead of maintaining the equal diameter as well as the equal height, by providing the taper, providing the taper, so that we can, since the velocity of the water is not uniform in the irrigation channel, the velocity of the water will be lower at the bottom side, that will be higher on the top side. So that to extract more velocity, instead of using the straight turbines, by modifying the turbine, we can extract the higher kinetic energy. And also by modifying the blade profile, by instead of using the conventional type, by modifying the blade profile into modified V shape. This is the V shape kind of turbine blade. This is a straight profile, and also small curvature is provided here, and also straight line. This is a type of V-shaped modified V-shaped type of turbine. And also, since we already discussed the turbine having the overlap ratio, will give the better results. So that by providing the overlap ratio for the optimum blade profile to increase the performance, that is also very important. And also, instead of using the two end plates, with the help of end plates, we'll get the better power. So compared to without end plate case, instead of using the two plates, if we use one more plate, which is exactly at the mid side of the turbine, so that we can extract a little bit improvement will be there in the, so compared to the two plate case. This is the application of using of the turbine in the case of the flat channel, and also in the case of the inclined channels. This is the turbine. The turbine which is placed in the irrigation channel. Total height of the turbine is HR. H is the height of the turbine, and this is connected to the dynamometer or generator to convert the hydrokinetic energy into electricity. And this is the D is the diameter of the turbine, H is the height of the turbine. The first picture shows a turbine placed in the horizontal case without inclination case. The second case, the turbine is placed in the inclined channel. That the this is the second case is known as the partially submerged. Since in the slope side, the depth of water will be less compared to the horizontal case, so that the turbine is partially submerged. The first case for the case of the flat channel, so that the theta will be 0 degree. The second case, theta is ranging from 0.5 degree to 2 degree, based on the locations of the irrigation channel. To find out the performance of the turbine, we need to create the irrigation channel scenario. Instead of conducting the actual turbine in the irrigation channel, first we develop the turbine with the help of the flume. This is the flume. This is known as a multi-purpose tilting flume. This flume is consisting of two tanks at the extreme ends of the channel. The turbine is placed exactly at far away from the inlet. The turbine is connected to the dynamometer to measure the torque. So water enters the flume from left side. The depth of the water can be measured with the help of the height gauge. With the help of the height gauge, we can measure what is the depth of water, and also the velocity of the water also we can measure with the help of any measuring instrument. Suppose if you are using the venturimeter, if you are using the any of the flow measuring instruments at the exit of the turbine, exit of the channel, by using the depth of the water, first we need to measure what is the wetted perimeter. At the exit of the flume, a rectangular notch will be used. With the help of a rectangular notch, we can calculate what is the discharge. By using the discharge, we can easily calculate what is the velocity. This is the simple setup to create the irrigation kind of scenario. The turbine is fixed to the test rig at the bottom. As the water enters the channel, because of due to the pressure difference between the advancing blade as well as the returning blade, the turbine will start rotating. After a turbine starts rotating, we have to apply the load. We have to apply the load to the shaft. This is similar to the IC engine setup to measure the torque. With the help of dynamometer, torque can be measured. With the help of torque, we need to measure what is the RPM of the shaft. With the help of RPM as well as the torque, we can easily calculate what is the power developed by the turbine. And also the same setup can be connected to the dynamo generator, so that we can get what is the conversion from hydrokinetic energy into electricity. This is the simple setup to conduct the experimental investigation for various kind of turbine, whether it may be without augmentation technique, with augmentation technique. We can easily measure, and also we can optimize the turbines to get the better results. We can measure what is the coefficient of torque. We can measure what is the coefficient of power. What is the power developed by the turbine can be find out by using the experimentation technique. This is the simple setup. And also this is the experimentation. By using the experimentation technique, we can measure what is the torque as well as the power. And also with the use of the same setup, we can create the slope. We can conduct the experiment for both horizontal case, and also we can conduct the experiment for various inclination. For example, 0.5 degree slope. What is, if you give the slope, what is the velocity of water and what is the power developed by the turbine? For various slopes, we can conduct what is the torque as well as the power with the use of the same setup. This setup is known as multi-purpose tilting flume. We can give the horizontal condition as well as the inclined condition. These are the simple analytical equations to calculate the various parameters like coefficient of torque as well as the coefficient of power and tip speed ratio. To find out these dimensionless parameter, we need only what is the RPM of the shaft. What is the RPM of the shaft, and what is the torque developed by the turbine. Torque developed by the turbine can be measured with the help of the dynamometer, and RPM we can measure, so that we can find out what is the conversion efficiency from the available energy in the irrigation channel, how much energy is converted into torque. With the use of these expressions, we can find out the coefficient of torque as well as the coefficient of power, and also the tip speed ratio. This is the by using the horizontal channel, and also by giving the slopes of 0.5 degree slope and 1 degree slope, 1.5 as well as 2 degree slope. We have conducted the various orientations of the channel. 0 degree to 2 degree is the coefficient of torque with respect to the tip speed ratio. For the case of 0.5 degree, the turbine is giving the better performance compared to 1 degree, 1.5 degree and 2 degree, because for the case of 1 degree, 1.5 and 2 degree, the energy available in the channel is very high and conversion efficiency is low, so that the coefficient of torque is reducing with respect to the inclination of the channel, so that the 0.5 degree inclination is giving the better results, so compared to the 1 degree, 1.5 degree and 2 degree inclinations. This is the variation of the velocity of the water with respect to the depth of water. As the depth of water velocity inclination of the channel increases, how the velocity varies with respect to the bed slope can be computed with the help of the Froude number. This is the this plot will give the variation of the torque available and torque power available for the case of the various flow numbers, because since it is a inclined channel, we need to develop we need to find out what is the flow number for various torque as well as the power developed by the turbine. So coming to the second type of turbine, this is known as by providing the taper to the normal conventional type of turbine. So how the performance influences, this is the schematic diagram of the conventional turbine. The second one is the taper turbine. And the conventional turbine, we already know it's consisting of advancing as well as the returning bed profile. In the case of taper turbine, the small taper will be provided on the right side of the turbine. A 5-degree turbine outside taper is provided 5 degree on the from top to the bottom, so that there is no uniformity in the diameter. From the top to bottom, the diameter of the turbine is varies, and also the aspect ratio maintained is 1 for both the case of conventional turbine as well as the taper turbine. The aspect ratio is remains same, and also there is no overlap ratio between the turbine advancing as well as the returning bed profile. This is the turbine with taper and without taper. To conduct various experimental by using the same experimentation technique, that is known as by using the tilting flume, we can conduct experimentation technique. We can find out what is the power developed by the turbine, and also by using the another technique, that is known as by using the numerical technique, we can find out what is the power as well as the torque developed by the turbine. To measure the torque as well as the power, first we need to create the computational domain similar to the irrigation channel. This is the channel we have created. Irrigation rectangular domain we have created. This is the turbine, and over this small zone is provided on the outer side of the turbine. That zone is known as rotating zone. Rotating zone is provided. This rectangular domain is similar to the irrigation channel. We have taken the rectangular domain. This is the front face of the domain. Here the water enters, and the rear face of the domain, water will leave. Since the irrigation channel consisting of 3 phases, one is the left face, right face, and the bottom face. So that various boundary conditions we have to give in the case of numerical analysis. Since 3 walls are there, bottom wall, 2, one is left wall, right wall, and bottom wall. So that for all the walls, the wall boundary conditions will be provided. For the case of the front, the velocity inlet is provided. For the case of rear side, pressure outlet boundary condition is provided. With the inlet velocity of 0.5 meter per second is provided, given to the channel. The water velocity is 0.5 meter per second. We need to give the RPM to the rotating zone. In the case of experimental, the turbine is rotating, we are measuring the RPM. But here we need to give the RPM. To give the RPM, we need to find out the tip speed ratio. With the help of the tip speed ratio, we have to compute what is the RPM of the shaft. So after creating the computational domain, we need to discretize the computational domain to find out the. We need to take the file to the fluent case. First, we have to discretize the computational domain. This is the meshing is provided over the entire computational domain for the case of rotating zone and also for the case of fixed zone. The meshes are varying the meshes for the case of fixed zone as well as the rotating zone. For the case of rotating zone, fine mesh will be provided to capture the more physics what is happening inside the rotating zone. We need to capture where the pressure is acting, maximum pressure is acting on the turbine, and what is the velocity of the fluid particle. Those things we need to measure. For this, fine mesh will be provided for the rotating zone, and coarse mesh will be provided for the fixed zone. This is the picture for the rotating zone as well as the fixed zone, and also expanded view of the image also shown here. And also the boundary layers will be provided. This is known as the inflation layer. To capture the boundary layer, the inflation layer will be also provided with a, by maintaining the y plus value is less than 1, 0.94 is given for the y plus value for the turbine. This is the figure number C is the expanded view of the turbine with inflation layers. This is the simple equations which is used to find out what is the RPM of the turbine. To first be in the ANSYS Fluent, we need to give the RPM. To find out the RPM, with the help of tip speed ratio, we can compute what is the RPM of the turbine by varying the tip speed ratio. For example, for the case of 0.7 TSR, as RPM of the turbine is around 92. So this RPM angular velocity we are giving to the turbine, and also since it is a numerical analysis, transient simulations is carried out with the help of the famous technique that is known as sliding mesh technique. For all the turbo machinery cases as well as the water turbine cases, sliding mesh technique is the famous technique which will give the accurate results compared to the steady case. It is a transient simulations, a three-dimensional transient simulation. There are two types of techniques are available. One is multiple reference frame technique. Second one is the sliding mesh technique. For the case of steady simulations, multiple reference frame technique will be used. For the case of transient simulation, sliding mesh technique will be used. Since it is a transient simulation, we need to give the time step. Time step also we have to compute to calculate the performance parameter. By using this simple expressions, we can find out the time step for one particular TSR. This is the values of time step size for the case of conventional turbine, and also for the case of taper turbine. For all the TSRs, tip speed ratio ranging from 0.7 to 1.3. This time step size we have to give as an input to find out the performance parameter for all the TSRs. And also these are the analytical equations to find out the torque as well as the power coefficients. Since it is a numerical study, before conducting the numerical study, we need to find out what is the optimum mesh elements. That is known as grid independent study we have to conduct. And also it is a since it is a time transient simulation, we have to conduct a time dependent study also by varying the number of elements to save the computational time. One optimum element will be taken for the simulation to reduce the computational time. So 19,87,000 elements have taken, and also time dependent study also conducted ranging from 0.5 degree, 1 degree, 2.5 up to 10 degree. For 10 degree to 2.5 degree, there is a huge variation in the results from one time steps to the one mesh element to the another mesh element. From 1 degree to 0.5 degree, there is no change in the values of coefficient of torque as well as the coefficient of power. So that 1 degree is taken as the best time step size to reduce the computational time for the CFD simulation. This is the results obtained by comparing the conventional turbine for taper turbine for the case of coefficient of torque as well as the coefficient of power. By providing the taper, by providing the taper of 0.5 degree, the turbine performance will be reduced, so that the conventional turbine without taper will give the better results compared to the taper turbine. So these are the simple results, that is known as pressure contours for the case of conventional turbine as well as the taper turbine. This is known as the high pressure zone for the case of advancing, for the case of conventional turbine as well as the taper turbine. For all the three views presented here, top view, side view, as well as the front view. Similarly, for the case of conventional, velocity contours also shown here. We can see here the high velocity zone is developed at the exit of the turbine in the case of taper turbine. So because of this, there is a loss of energy is happening in the case of taper turbine. Because of this, the turbine performance reducing for the case of taper turbine. Because of due to the loss of energy, the turbine performance is reducing. We can find out with the help of this velocity contours. To increase the performance of the turbine, another technique is by modifying the blade profile into a modified version by converting the conventional blade profile. Conventional blade profile consisting of semicircular blade profile. Converting the semicircular blade profile into a modified version. Since we need to increase the performance, this is the another technique in the recent developments of the vertical axis turbine, especially for the case of Savonius turbines. This is the one of the technique to improve the performance, that is by modifying the blade profile, that is converting the conventional blade profile into modified version. Various researchers converted the conventional blade profile into a modified version by, this is the one of the example taken from the source, the conversion of one stage to the final stage. This is the final stage, that is V4. V4 is the modified version of the blade profile. V1 to V4, these are the various stages of conversion from conventional to the modified version. For this case also, they conducted numerical study, and also they optimized the results. These are the comparison of the conventional blade profile to the modified version. The modified version is having better results compared to the conventional. Like these are the pressure contours for a conventional blade profile as well as the modified version. By providing the overlap ratio, between the advancing blade as well as the returning blade, which increases the performance. These are the one of the examples by providing the overlap ratio to increase the performance of the turbine. A small gap will be provided. Small e is known as the gap, which is provided between the advancing blade as well as the returning blade. By providing the overlap ratio, that is a small gap, the turbine diameter also reduces, so that the turbine performance reduces. If we give the overlap ratio, if we maintain the same diameter, this is the same velocity contours for the case of turbine without overlap ratio and turbine with overlap ratio. This is the small jet kind of thing is obtained, developed between the advancing blade as well as the returning blade. This jet is not impinging on the right side of the turbine, so that turbine performance in this case, in the case of the modified version, by providing the overlap ratio, the turbine performance is not improving in the case of the modified V-shaped blade profile. So another technique by changing the blade angle. By changing the blade angle, that is the one of the technique to improve the performance by varying the blade angle, a modified V blade profile. Instead of maintaining the 90 degree, various researchers conducted the by giving the different angles ranging from 90 to 40 degree by giving this inclination. These are the various geometries of the turbines with different angle of inclination. First one, for the case of angle between the advancing the straight profiles is 90 degree, 80 degree range, like that. Various angle of inclination is provided, and they have conducted the similar kind of the numerical study as well as the experimental study to find out the performance parameter. These are the various results obtained during the after experimentation for all the inclinations. For this 90 degree, 80 degree inclination will giving the better results compared to the remaining inclinations of the advancing blade profile inclination. Because of advancing blade, in this case we can see the advancing returning blade is almost similar to the semicircular case, so that whatever the fluid is acting is directly acting on the returning blade profile. More drag will be generated in this area, that is more drag will be developed on the returning blade profile. Therefore the turbine performance is reduces for all the remaining cases compared to the 80 degree inclination. These are the similar kind of results obtained with the help of pressure contours on the for the case of 80 degree, giving the better results compared to the previous case. For different inclinations, they have taken this picture for 0 degree. This is the initial position when the turbine is rotating at an angle of 26 degree. This is the high pressure zone. The high pressure is fluid is acting on the returning blade profile, then more drag is developed on this particular angle, 26 degree, so that at this angle negative torque will be developed. At an angle of 109 degree, 109 degree, the pressure difference between the advancing blade and the returning blade will be higher, so that the maximum pressure is developed on the advancing blade profile, so that the more torque will be developed in the case of 109 degree, so that the average torque will be improved for the case of 80 degree case of blade profile. This is the similar kind of numerical analysis velocity contour plots for the case of this is the high velocity zone which is developed at the tip of the blade profile. This is known as high velocity zone. On the right side of the turbine, another zone is developed that is known as wake zone. This wake zone is very important while installing the turbine in the actual practice, like in the irrigation channels. When the distance between first turbine to the second turbine is very close, so that the turbine performance will reduces. So that with the help of this wake zone, while installing the turbine in the actual irrigation channels, we need to maintain certain distance to get the equal production of electricity from each turbine, to maintain some certain distance from one turbine to the another turbine. From this we can get how to install the turbines in the irrigation channels. So another technique, that is with the help of 3 plates, turbine performance can be improved. Experimentation techniques conducted with the help of turbine having the 2 plates and turbine having 3 plates by maintaining the by varying the aspect ratio. This is the pictorial picture for both turbine with 2 plates having and also turbine with 3 plates. This is the various parameters studied for all the aspect ratios for the 2 plate case, for all the aspect ratio for 3 plates. Thus all the turbines are tested in the test rig to find out the optimum aspect ratio and also to find out the optimum end plates, which blade will give the better results. All the turbines are conducted. This is the pictorial for actual turbines fabricated for the experimentation for all the aspect ratios ranging from 0.7 to 1.75 for 2 plates as well as the 3 plates. Top plate is the middle plate is known as exactly placed at the midpoint of the turbine. The thickness of the turbine as well as the end plates are almost the same, almost 1 millimeter thickness maintained. See, this turbine is fixed to the test rig. This is the test rig. The turbine is connected to the shaft. The shaft is connected to the rope. With the help of this is the simple mechanism that is known as rope type of dynamometer to measure the torque. Various dynamometers are available. We can use the different types of dynamometers also. This is the expanded view of the turbine placed in the irrigation channel. The same test rig placed in the multi-purpose tilting flume to conduct the similar kind of experimentation. Total height of the turbine is around 15 centimeter. 15 centimeter was the height of the turbine. The total depth of water is around 17 centimeter depth of water maintained because all the turbines are conducted at fully submerged condition. Fully submerged condition, all the turbines are tested. So by varying the aspect ratio, as the aspect ratio increases, turbine performance also increasing. We can see from these two graphs, as the aspect ratio increases from 0.7 to 1.75, the turbine performance also increasing. The last case, the aspect ratio of 0.75 is giving the better results compared to the 0.71 and 1.5 case. And also turbine with 3 plates. Turbine with 3 plates is having the better in performance compared to 2 plates, so that we can recommend a turbine having 3 plates is giving the better performance compared to the 2 plates turbine case. And also various by adding the one more advancing bed profiles for the already existing advancing bed profile, how the turbine behaves. If you provide the one more additional advancing blades, this is the schematic diagram for turbine having 3 advancing blades as well as the 2 advancing blade and 3 advancing blade. For this case also, experimentation as well as the numerical study conducted by using the same test rig, multi-purpose tilting flume. This is the numerical model to conduct the experimentation investigation for 3-dimensional study. This is for the case of two-bladed turbine having 2 end plates. This is for a 3-bladed turbine. Number of blades will be 3 in this case. This is for the case of turbine having 2 advancing blade and 2 returning blades. This is the we can see in the previous case. This is the line diagram for turbine having the 2 advancing blades and also turbine having the 3 advancing blades. So one more study conducted to find out how, suppose if we vary the diameter of the advancing blade, how the turbine performance increases, how to find out the turbine performance. This is the another case by comparing the turbines with various diameter of the advancing blade as well as the returning blade by increasing the number of blades. This the last one is known as 6-bladed turbine. Similar kind of numerical study is conducted for this case also. From this we can find out, this is the one of the plot that is known as polar plot. With the help of this polar plot, we can identify at what angle of rotation the turbine is giving the negative torque. To reduce the negative torque, how to improve the turbine efficiency, we can study it with the help of this plot. This is known as the polar plot. By using this polar plot, the variation of torque with respect to angle of rotation can be found out with the help of this polar plot. Another plot is known as the variation of torque with respect to quotient of torque. See, at an angle of 115 degree, the turbine is giving the maximum torque. The turbine is giving the maximum torque. This is the maximum torque region. This region is known as maximum torque region. And also similarly, the outer two extreme sides of the plot is for the case of the maximum torque region, and two inner zone of the picture will give the negative torque region. So in the case of negative torque, this is the picture for the negative torque. Here the fluid is impinging on the advancing blade, so that the maximum pressure is generated at the returning blade side, so that the turbine performance is reduces. With the help of this plot, we can find out which angle of rotation the turbine is giving the better torque with the help of polar plot. This is the this plot is for the case of two-bladed turbine. Similarly, for the case of four-bladed turbine, see in this easily we can identify a turbine having more than two blades. A turbine having the more than two blades, at everywhere it is most of the cases it is generating the negative torque. The more negative torque will be developed in the case of the four-bladed turbine, so that the two-bladed turbine is the better performance compared to the remaining blade profiles. This is the same polar plot for the case of four-bladed turbine. Similarly, for the case of by varying the advancing blade profiles, by reducing the third and fourth advancing blade, how the turbine performance varies. This is the schematic diagram. In this case also, turbine performance is lesser, and also more negative torque will be generated in this case compared to the two-bladed turbine. This is also another two advancing blade profiles will be provided on the same turbine. How the addition of two-bladed turbines with the help of small advancing blade profiles influences the turbine performance can be find out with the help of this polar plot. And similarly, this is the last case. By increasing the number of plates, how the negative torque will be influences the turbine performance. Here many lower zones are there, and also many higher pressure zones are there. The overall average torque of the turbine is lesser compared to the two-bladed turbine. We can see here in the most of the cases negative torque obtained from this picture. The total average torque will be lower compared to the two-bladed conventional turbine blade profiles. And also, instead of installing the turbines, the Savonius kind of turbine in the straight channels, if we install the turbines in the case of the bent channels, because in most of the cases the channels will not be the straight case. In the some of the places the curvature will be there, so that before installing the turbine in the channel with the various bent channels, we have conducted the numerical study to find out which angle of rotation or which angle of channel bend will give the better results. This is the similar kind of channel with different bend angles ranging from 30 degree. This is the exact 90 degree bend channel. 90 degree bend channel, also 60 degree bend, and also the 30 degree bend. The inside curvature will be 90 degree, 60 degree, and also the 30 degree. We have conducted the 3D numerical analysis for the case of straight channel, and also 90 degree bend channel, 60 and 30 degree. Out of these four different channels, in which case we have to install the turbine, either in the straight channel or in the bend channel, because in the curvature the water will be easily hitting the advancing blade profile, so that the turbine performance can be improved. This is the overall idea to improve the performance of the turbine. And this is the schematic diagram of the channel. having a straight channel and also 90-degree bend. This is the wall of the channel, two side walls, and one is the bottom surface. This is the turbine is placed exactly at the center. Because why we placed the turbine exactly at the center? Because at the wall side, the velocity of the water will be less, because of due to the no slip condition, the velocity is very less at the wall side, so that the water velocity will be higher exactly at the midpoint of the channel, the center line of the channel, so that in all the cases the turbine is exactly placed at the midpoint of the channel. This is the schematic diagram of the turbine having the straight design and also 90-degree bend design. To conduct the numerical study for all the angles, straight channel, 30 degree, 60 degree, as well as the 90 degree, 3D model is created. That is, 3D computational domain is created for the case of the bend channel. This is the one of the schematic diagram of the 3D model for the bend channel. The advancing blade is This is the advancing blade is nearer to the curvature. Whatever the fluid enters, that will be hitting on the advancing blade profile. Suppose if we use instead of the pressure outlet, if we use the inlet, the turbine performance will be reduces. This condition also we have carried out. Suppose if we use inlet condition in the place of pressure outlet, how the turbine performance will be influences. This is the optimum design to place the turbine in the bend channel case. This is the position of the advancing blade profile. Always the advancing blade profile should be nearer to the curvature side. This is the 3D model of the bend channel. The similar boundary conditions we have provided here. 3 wall boundary condition, one for left wall, right wall, as well as the bottom wall, and the velocity inlet as well as the velocity outlet boundary condition is provided. By maintaining the water velocity, uniform water velocity of 0.5 meter per second is maintained, and also top surface is exposed to the atmosphere. Since the top surface is exposed to the atmosphere, the boundary condition provided at the top side is the symmetry boundary condition. There is no change in the values of velocity at the top side, so that the symmetry boundary condition is provided in the top side. We need to give the RPM to the shaft with the help of the tip speed ratio, RPM as well as the angular velocity can be obtained and can be given as an input to the turbine. And also similar to the previous case, we need to discretize the computational domain. The fine mesh will be provided to the rotating zone, and the coarse mesh will be provided to the stationary zone. Almost around 35 lakh elements we have got in this entire computational domain, so that the high-end computational facility we have used with the help of high-end computational facility only we can perform the numerical simulation. This is the rotating zone, stationary zone, and also this is the expanded view of the boundary layer. The boundary layer also provided on the surface of the blade profiles by maintaining the y plus value of less than 1. And also since it is a rotating case, it is not a laminar case, it is a turbulent case. SSD K omega model. SSD K omega model will be used for the case of turbulent case. For most of the rotating cases, as well as the flow over a aerofoil case, for all the cases, SSD K omega model will give the better results compared to the K epsilon model and different types of turbulence model. SSD K omega model will give the better results compared to the various types of other models. This is the comparison of straight channel with 30 degree, 60 degree, and 90 degree. This plot will give the variation of coefficient of power as well as the coefficient of torque. This is the coefficient of power variation plot. In this case, 30-degree bend channel. 30-degree bend channel is giving the better results compared to a straight channel as well as 60-degree and 90-degree channel. So that installing the turbines in the 30-degree inclination and also by maintaining the advancing blade nearer to the curvature, it will give the improved performance. This is the numerical analysis of plots, that is a pressure contour plots for the case of various bend channels at an angle of 110 degree. 110 degree, the torque developed by the turbine is higher at an angle of 110 degree, so that the higher pressure zone is developed at the advancing blade profile side. This is the higher pressure zone. This is the variation of pressure ranging from minus 912, 9712 or 273 Pascal at an angle of 110 degree. The advancing blade profile at an angle of 110 degree, the pressure difference between the advancing and returning blade profile is higher for this particular case for a bend angle of 90 degree. And similarly, for the bend angle of 30 degree, at an angle of 112 degree, the maximum torque developed by the turbine is higher at an angle of rotation of the 112 degree, because during the rotation of the turbine, at some angle of rotation, the turbine will give the negative torque. At some angle of rotation, a turbine will develop the positive torque. For this particular angle, 112 degree angle, the turbine will develop the higher positive torque. Then overall performance of the turbine will be higher in this case, so that the average torque also higher for the case of 30 degree bend angle. Similarly, the same plot for at an angle of 285 degree. This is for the case of 60 degree bend angle. For 60 degree bend angle, this is the maximum torque. The overall torque is still lower than the 30 degree bend angle. For the case of 30 degree bend angle, the fluid is directly hitting on the advancing blade profile because of due to the curvature of the channel, so that even if we use 60 degree and 90 degree, the turbine performance for the case of 30 degree bend angle is higher compared to straight channel 90 and 60 degree channel. This is the velocity contour plots for the case of 90 degree bend channel. This is the wake zone. Wake zone is developed at the rear side of the channel. This is the direction of rotation of the channel. The turbine is rotating in the anti-clockwise direction. This is the direction of the fluid flow. The fluid enters and fluid leaves at an angle of 110 degree. The high velocity is zone is developed at the rear side of the blade profile. And similarly, for the case of 60 degree, this is the velocity contour plots for the case of 60 degree bend channel at an angle of 285 degree. This is the direction of rotation of the channel and direction of the fluid flow. And similarly, at an angle of 112 degree, this is the optimum angle we have found for all the four cases. 30 degree bend angle is giving the better results compared to the straight channel 90 degree bend channel as well as the 60 degree bend channel. And also with the help of this streamlined plots, we can analyze which direction the fluid is flowing and where the fluid is acting on the advancing bed profiles can be analyzed with the help of this streamlined plots. This is for the case of 90 degree channel. The high velocity zone is developed at the advancing tip of the advancing bed profile and also at the exit of the turbine, at the rear side of the turbine. This zone is the highly turbulent zone. This is known as the turbulent region. That's why we are using the turbulence model for all the case of simulation at an angle of rotation angle of 196 degree for a bend angle of 90 degree. This is the streamline plots for the case of 90 degree bend channel. Similarly, for the case of 60 degree bend channel, this is the plots, contour plots, sorry, streamline plots for the case of bend channel with an angle of 60 degree. And for the case of 30 degree bend channel, this is the streamline plots. By using these plots, we can analyze where the fluid is impinging on the turbine. With the help of these plots, we can optimize the turbine. A similar kind of optimized kind of turbine can be installed in the irrigation channels to develop the small scale electricity that will be useful for the rural areas. So with on an average of 3 feet into 2 feet diameter turbine, if we installed in the actual irrigation channel, so that we can develop a small scale electricity that will be helpful to generate to operate a motor pumps, as well as, and also that those electricity will be useful for the village areas to use street lights. This is the idea of this kind of vertical axis turbine, Savonius turbine. With the help of this Savonius turbine, installing in the case of irrigation channels where the electricity is not there in the rural places, a small scale electricity can be generated. So that electricity can be useful for the rural areas to generate the small scale electricity. This is the idea of this vertical axis hydrokinetic turbine. These are the recent advancement developed in the case of vertical axis by converting the normal conventional turbine. Previously, it was a semicircular kind of turbine. So that semicircular kind of turbine can be in the coefficient of torque and power for the old conventional type of turbine was 0.25. By modifying the blade profile into various shape, the performance was improved by around 60%. Performance improved happened by converting the conventional blade profile into a modified version. So that if we install the modified version in the actual irrigation channel, see whatever the models we have created, these are all the scaled down model. For the laboratory conditions, we have developed these kind of models. If we improve the dimensions as per the size of the irrigation channels, and also if we measure what is the velocity of the water in the actual irrigation channels, around on an average up to 2 meter per second velocity we will get in the actual irrigation channels, so that we can get a very good power generation can be obtained if we install these kind of turbines in the actual irrigation channels, so that we can give the electricity to the rural people, so that we can improve the efficiency of the turbine. So thank you.
Participants, if you have any questions, please ask to Dr. Shashikumar sir. Stop presenting, sir. Just yeah, there you click, sir. Tabish, you can ask the question.
Hi, Sachi sir. It's nice presentation.
Hi, sir.
Informative session. Okay, just to carry on line, what I understood from the research is you have a different bend angles, and you're trying to optimize this, right?
Yeah.
Okay, I find some vague reason beyond your rotation. So what you did is was dynamic mesh rotation.
Yeah, it is a rotating mesh.
A rotating
Whole
mesh.
mesh.
Okay. So the wake region where the pressure is very low,
Velocity is low.
velocity is low. Velocity is low or pressure is low.
Velocity.
So do you have ever faced a back pressure kind of thing somewhere?
So back pressure kind of thing is not there here. The main use of this wake zone while installing the turbines in the grid manner, like in the case of series or parallel manner, we need to place the turbine from one turbine to the next turbine. We need to maintain certain distance. That is the one of the advantage of finding out the wake zone.
Okay. Have you any do like in comparison how much if you increase the wake region or a low velocity region somehow do you get
Suppose
some
if we install the turbine from one turbine to the next turbine in a closer manner, the first turbine will generating the higher power, the next turbine will generating the lower power. Because the next turbine is nearer to the wake zone, that is a low velocity zone. So that with the help of low velocity turbine also will develop the low velocity, low power.
Okay, yeah, that's it. Thank you for clearing the doubt. Thank you so much.
Manish sir, if you have a question, I think you can ask.
Hello, sir.
Hello, sir.
Sir, you have shown, I think, almost two types of turbine that top and bottom end and without end.
Yeah, end plates and without end plate case.
Without end plates.
Yeah.
So, have you studied the effect of head on end plate turbine?
Yeah. Because end plate, the turbine with end plate will give the better efficiency compared to without end plate case. Because with the use of end plate, the turbine will hold the fluid during the rotation of the turbine. The advancing blade will hold the fluid during the rotation of the turbine, so that the overall efficiency can be improved.
No, so
We
my
have
question is
conducted.
that I am asking, have you studied? Suppose if the end plate is fully submerged in a channel.
Because all the cases the turbine should be fully submerged, because if the turbine is partially submerged, the performance will be reduced. In all the cases, turbine should be fully submerged condition.
Sir, I am asking regarding the effect of head on the performance of turbine.
Effect of
head. Suppose there is a water head.
Yeah. Because it is a low head turbine. These turbines will work on the low head case also. That's why this Savonius turbine can be used. This is a drag type device. This will work at low velocity also.
Okay, sir.
Because the normal conventional type of turbines like a Pelton turbine, Kaplan turbine, for all the cases head is required. For this, that much head is not required. That is known as low head turbine. This turbine is also known as low head case of turbine.
Okay, participants, any other questions?
One more, please share the slide with us, sir.
Sir?
Because to share the slide.
Sure. I will share this slide to coordinator.
Because as we have a test on the Saturday.
Sure, sir. We will share the slide to the coordinator.
Definitely, sir. We will share the all the information to participants. Okay, sir.
Okay, thank you, sir.
Welcome, sir. Hello, sir. Hello, sir. Good evening, sir. Hello, am I?
Sir, hope I'm audible.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, hi Shashidhar sir, how are you?
I'm fine, sir.
Yeah, thank you. I'm sorry I'm not able to attend your session. Anyhow, I'm a part of the participant of this FDP.
Yes, sir.
But then due to traveling conditions, just now only I reached home.
Okay.
I'm not able to attend. So let us see in the future time.
Sure, sir.
I
I will
wanted
share
to
the PPT to the Dr. Madhu, sir. We can go.
Yes, sure, sir. Thank you very much.
Okay, sir. You can.
Thank you, Chitragar sir. Dr. Shashikumar sir. Sir, you have any questions, sir?
I'm able to talk to Tabish Wahidi sir right now, if he's on the platform.
Yes, sir. Yes, go ahead, sir.
Yes.
Tabish sir, just even I missed your session also. Partly I'm unable to attend your session. But then I'm curious to know in what way can I get the help of US for my students. I'm interested to develop a kind of knowledge on electrical vehicles along my students.
Okay. So we can collaborate,
in
sir.
what way?
I can help you guys to, in the term of simulation things, and give you an overview how can we start all these things. That I can help you out. It's not a problem. If you come with a specific problem, then it will be quite easy for me to understand and proceed.
Okay, thanks for that one. And in fact, I would like to say our institute has become autonomous from last 2 years.
Okay.
In that situation, even we are going ahead with this NEP program. I mean NEP implementation in the syllabus of autonomy. Wherein in final year we would like to send our students for internship for whole 1 semester for 6 months.
Okay, that we can look into. You must have an MOU with our organization, so that we can hire them for 6 months of training internally, and we can train them as per your requirement and as per the syllabus. If you have something specific.
Yes, that's what I wanted to know from your side.
That I have to look into with the team. Exactly, I'm not the decision maker for this one, but it's possible from as per my information.
Yeah. Thanks for your assurance, sir. We'll be in touch, and then I'll contact you later, sir.
Sure, sir. Thanks, sir.
Yeah. Thank you.
Thank you, Tabish and Dr. Parshuram Chitragar sir. And first of all, I should thank to Dr. Shashikumar CM sir. He has given the nice presentation. He has delivered the session very nicely from basic to the applications and different efficiency, how we can increase with the Savonius turbine. As currently we are talking about the energy sustainability and climate change. I think sir has given the right path to utilize the turbine, even for the like a low head. For the irrigation purpose, if you use these turbine also, you can generate the power and you can utilize for the different application instead of even yesterday I was talking about the hydroelectric power. So there we require the maximum height. Height require more for the turbines, for the Kaplan, or it may be different types of turbines. So that we can avoid and we can generate in a even every level of the society. So which will again mitigate of the requirement of the energy to the world. So thank you, sir. It was a really nice session. I hope all the participants they have understood your sections, and definitely it would help them to continue with the research also. So again, it will be more helpful for all the industry as well as academic fraternity. Thank you very much, sir.
So thank you, sir. Thank you for giving this opportunity to share my knowledge. Thank you for the coordinators and Nutan Maharashtra College of Engineering and Technology, and also AICT for giving this platform to present my knowledge and share my knowledge. Thank you, sir.
Thank you very much, sir. So participants, now it's time to end the session. So again, for tomorrow we have 2 more sessions, which will start at again 6 p.m. 6 p.m. to 7:30 and 7:30 to 9. We have a different as per the schedule. We have the topic of hydrogen economy and also mechanical operations, which are suffering in the industry. So that we are going to see in coming sessions. So I hope everyone will join for the tomorrow. We will have the better attendance also. Thank you very much all. I say good night to all. Thank you.
Hello, Mukunda sir.
हाँ मनीष सर बोलिए सर.
I request to say the slide which you have with you, please share with us.
Yes sir, but for the test purpose actually like a few of the session chairs, they have the confidential. So there is a little problem with the sharing the slides, sir. And the remaining, those who are really if we get the information from the speakers, definitely we'll share with you people, sir. No problem, sir.
Okay, thank you, sir.
Because a few of them are working in the industry as well as in a government organization. There it is difficult to share the slides with all the people. So that's why, sir. Okay.
Okay, sir.
Okay. Thank you. I think Manish Kumar sir, you have you are attending very attentively. Thank you very much.
Thank you, sir.
Okay. Good night all.